And we now go on with the agenda, and our next speaker is Matthias Sonder from Teledyne, who will speak about multi-information imaging technologies.
All right. Is that okay? It's working. Very good.
The stage is yours.
Yeah, we can start. Do I have to press this, or how does it start? Okay. Excellent. So, good morning, I guess, everybody. Matthias Sonder, Teledyne DALSA. It was a very nice introduction to TDI. I have a little bit of this as well, but I wanted to talk a little bit about a discussion that interestingly came up several times over the last few months. Customers asking, well, when do I use 2D and when do I use low noise CMOS, like an area sensor low noise? So I wanted to share with you a bit of the thought process that we go through to help you, customers, to make that choice. And I do this by sort of sharing with you two products and working through them. So this is an ultra low noise CMOS camera that Teledyne has just recently released. And the idea there is basically we're trying to bring the speed of these devices up. So you see on the x-axis the line time, and we're bringing the noise down. So that's kind of the trend of this whole ultra low noise CMOS concept, that the noise comes down, and if you're following this a little bit, you've probably seen announcements, single electrons, below single electrons, photon counting. This is all kind of the same idea. And it requires specific methods of achieving this kind of performance. I will talk about this a little bit. The one thing I wanted to maybe clarify a little bit, the way I think about this is there's a few categories of performance levels that we should consider. There's maybe normal sensors, and I place them here kind of above 3 electrons of noise. Those are typical devices you can get today. And then I put low noise there, which is, I kind of arbitrarily picked those numbers, but it's between 1 and 3 electrons. You already have to do a few special things to get to those levels. You have to have high precision ADCs. You have to maybe increase your reset times. You have to do a bit of better sampling in the chip. You basically increase your frame overhead time, so the chip becomes a little slower. You maybe suffer some full well. The full wells are not as high as they could be, and overall your frame rate goes down. And then you go into the really low noise, the ultra low noise regime, so under the 1 electron of noise, and you pick your number there, where we have to do things like multiple reads, multiple frame captures, averaging, whatever it might be. So you typically end up with lower full wells still, and of course with much lower frame rates. And just to illustrate that, you see the graph there, where if you have sort of this M factor on the x-axis, is basically a multiple frame operation, and you see how that decreases your noise level, your dark noise, your readout noise level. And you can imagine that reading out 10 frames, of course, slows your system down quite a bit. That's what I mean by this. As a product concept, as I mentioned, the recently released the Teledyne Cosmos camera. It's available up to 64 megapixels. And it operates in these low and ultra low noise regimes. This particular model is deep cooling capable for scientific applications. That's I just used it as an example here. But I do want to point out the low dark current is of course very interesting for long exposure times. We'll come back to this. You see the full well there, 12,000 electrons in the high gain mode, which is also the low noise mode. In the low gain mode, it actually has quite a high full well, but you can also see the noise number, 1.5 electrons versus 13 electrons, 14 electrons. So you see the difference there, the impact of that choice. And the last note I want to make is the pixel rate. The speed for this device, 1.5 gigapixels. Keep that in mind. We'll come back to this as well. It's relatively fast, but it's of course not as fast as things go today, as you've also heard before. So these ultra-low noise technologies take some time. Now I want to contrast this with TDI. So this is, of course, some images of that, and the concept, we've already seen this before. On the bottom right, you see the same concept. You have basically an object moving exactly once. Sorry for that. So the object moved from the top to the bottom. The idea is every time you have another line that you acquire, the object collects some more photons and gets brighter and brighter, as we've also seen before. And what this means is every object is basically sampled n times. So you have n lines, you get n times the sample rate, n times the sampling, you get the signal summing, it's all noise-free, and this allows you actually to have a high full well. Both technically, you can have a high full well in the sensor, but you can actually also fill that full well because you have n times the integration effectively, and that means you actually can collect enough photons to use your full well. You don't just have a full well and end up with a low signal level. So the effect is effectively, like I said there, like having n times the integration time. So that's how we create this higher sensitivity. Another little benefit is that you can actually maximize your image circle for resolution. Right? You can fit as many. It's a line scan sensor, so you can fit as many pixels as possible in the circle of the lens. You don't have to share it in a diagonal with a two-dimensional sensor. That's a bit of an advantage. You get more pixels for the lens cost, but you have to scan, obviously. And the product for this, of course, we have the Teledyne linear. You've heard other product options there. We offer this whole scanning scenario from 2K to 32K cameras, 400 plus line rates, and multi-array solution, different pixel sizes. You come to the booth, we can walk you through all of this. But for this discussion, we have the 30,000 electrons full well, so this is what our TDI camera has. You see the noise is about 9 electrons, so it's not in the realm of low noise, it's in the realm of normal noise. And we will see in a minute what that actually means for applications. And then you have the gain, which is basically the number of stages, right? So in line scan cameras on the right, we have maybe 1 to 4 stages. We have a bit different full wells, different noises, mostly a single pixel application. On the TDI side, you have the n pixels, so the summing, and this goes from something like 16 to 256. And then the pixel rate, I wanted to draw your attention to this. We are on the order, they are 10 times faster than the low noise CMOS was, right? We were at 1.5, now we are at 13 gigapixels per second. So then let me talk a little bit about the performance thinking that we go through when a customer comes with this and asks these questions. I always like to have these plots, and I've seen them several times now, so it's nice that others are using this idea. We have on the y-axis the SNR. The way I like to think about it is the SNR that your system can achieve. And your system is actually on the x-axis. So if you have a certain light power, and you have a certain speed or integration time, and optics and everything in between, then you end up with a certain light energy that is available for imaging in your system. So that's on the x-axis. So you can position yourself somewhere like, let's say, at 10, which you derive from your system, and you say, okay, if I have a light energy of 10 available for my imaging scenario, which sensor will give me the SNR that I need? And then, you say on the y-axis, you say, okay, I need 10. So I'm going to make a cross line there, and I say, so for 10 picojoule per centimeter square, the low noise CMOS sensor will give me an SNR of 2. Sorry, not enough. A line scan sensor will give me nothing. So I have absolutely no contrast in an image. And a TDI sensor in this particular picture will give you, because of the summing behavior, it'll give you a nice high signal to noise ratio. So that's the idea of TDI. But I need to qualify this a little bit, because the integration time is something we need to consider. So if I plot this a little different, and I plot the exposure time on the x-axis and the signal to noise ratio that we achieve on the y-axis, then if I just do a straight calculation comparison, like I said, a TDI has 128, 256 stages, so the exposure time is accordingly longer. Of course, the signal to noise ratio is higher. However, this is not quite the fair comparison, because what really happens here is if I go to a real system, in a real system, you will come and say, well, I need 2,000 lines of image data in 10 milliseconds, as an example. With an area sensor, you take one snapshot in 10 milliseconds, and you got your data effectively. With a scanning system, you need to take 2,000 lines in 10 milliseconds, which means it takes 5 microseconds per line. So your integration time for a line scan sensor, for a TDI sensor, is actually 5 microseconds, which is a lot shorter than 10 milliseconds. with an area sensor, with an ultra-low noise sensor, you can potentially integrate for 10 milliseconds. But now you have to do something on the system side, right? So the first comparison is when we look at the exposure time and we say, okay, well, how long can I expose? Then in these 10 milliseconds for 2,000 rows, then of course my TDI is now fixed signal-to-noise ratio because it's 10 milliseconds, it's 5 microseconds per row summed by the number of stages. But the area sensor integrates these 2,000 lines in one shot. So if I can afford a 10 milliseconds integration time, my SNR goes all the way to the right and up. So that obviously looks very good. So the question then comes, well, what stops me from integrating so long? And that's mostly motion tolerance. So if you have a moving system, then you cannot integrate for 10 milliseconds because everything becomes a blur. So what happens then is we build start-stop systems. So we take a table, we take our object, we move it in place, we hold it there, we take the images, and then we move it on and bring in a new object. That's what we call a start-stop system. That's great if you're using an area sensor and you need motion stabilized long integration times. That's what you have to do. And now comes the question, well, how fast can you do that? Right? So if you decide you want to move an object in place, you stop it, you have to accelerate, you have to decelerate, you have to wait until the whole system stabilizes, and this takes you time. And if that time is short, by all means, let's go and do this, and then we can actually get a relatively high SNR without wasting time. And that's what you see on the left side. So in this picture now, you see that the area sensors, the ultra-low noise CMOS sensor, has a stable SNR because the integration time is always 10 milliseconds, and the start-stop time just goes on top of that. But if you consider a certain amount of start and stop overhead on the x-axis, if it's very low, then so sorry, one more piece. The TDI, of course, if I have time to start and stop my system, then in that time I can also just slow down the system and basically increase my integration time on the TDI sensor and make that one more sensitive. And that's what I'm trying to say here in this graph. If you have an overhead time that's 0, then a start-stop system is the winner in this scenario. But if you do have a start-stop time that is 10 milliseconds, then you can do two things. You can actually use the 10 milliseconds and integrate, or you can slow your system down and provide the TDI sensor twice the integration time. And then you have almost a matched scenario there. And if your overhead becomes even longer, then again, you're always better off using a scanning approach and slowing your system down and not worrying about start and stop. And this is kind of the thought process that we need to go through in these scenarios. And then with that, I think I just want to make a quick jump over to the multi-information. That's where we started the topic. The idea then is, okay, so there's also this trend of multi-information. So per imaging station, you need more than just a black and white image. You need color, you need high dynamic range. Nowadays, there's spectral, there's angle, there's super resolution, there's polarization, there's all kinds of things that people want to see. And that usually means you need to take more images per object. And in a line scan scenario, we have these multi-array sensors, both line scan and TDI. You basically get that information in one scan. In an area system, you can do it the same way. You just take multiple light sources and take multiple snapshots. If you have a start-stop system, that's great because your object is already stopped. And if it took you 20 milliseconds to stop, now you take 4 images and you've increased your efficiency again, your data throughput basically. And that's kind of sort of a fundamental difference for how you have to do this with these two devices, but it can be done and it's very attractive. In the line scan sensor concept and in some area sensors, of course, we employ different filter techniques. You see effectively the different forms of dichroic and organic filter mixes. And on the right side, you see polarizers, nanogrids, nanostructures on the sensor. Those are all ways of increasing the information content. So then to close this, last but not least, the two systems exist next to each other, and you come and visit us, you will see them side by side. TDI, in my opinion, has benefits in general systems throughput. You have it easier to have fast-running systems. You have more light sensitivity due to the summing effects. You have the native multi-information system. You don't have to do anything with light sources. We can do a lot of it for you on the sensor. And of course, you have this effectively the photon summing effect, which enables shorter takt times in your system. The ultra-low noise CMOS sensors are, in my opinion, by far the highest performance area sensors you can find nowadays. They support snapshot imaging at really low noise. They enable the multi-frame solution, like I explained, in a start-stop system. And the low noise and specifically the low dark current enables long exposure times, so you can actually have really nice long exposure to, for example, overcome dark imaging challenges. And with that, I thank you for your attention, and we have a bit of time left.
Okay, thank you very much.
Thanks.
The room is also open for questions. Please feel free to ask.
No questions?
Oh, there. Could you please be so kind?
I had to be the opposite side to the microphone. On the ultra-low noise, is there a limit to pixel size, how small you can get the pixel sizes down? Or pitch? Or
not in principle. I mean, we've heard about 3D stacking technologies, so there's a lot of ways we can overcome challenges in small pixel sizes. Physically, there's always a limit to pixel size, right? If it gets too small, you have a limitation. If it gets too large, you have a limitation. But there have been announcements for single micron pixels, so they can be very small.
No, the more sensitive camera is always larger pixel.
Yes. So
I design lenses, so I'm interested in the sensitivity per square micron.
Yeah, so obviously the sensitivity of small, if you want a high sensitivity camera, starting with the smallest possible pixel is maybe not the right answer. So, right, so I think that's an obvious statement. And since if you design lenses, my experience is it's actually very difficult to make good lenses for really small pixels. So we as a camera manufacturer like to talk to lens manufacturers to see what's possible, and that's why you don't really see very extreme pixel sizes, because this is the guidance we get from system developers, what's actually possible and what makes sense. So technically a lot more is possible, but not everything that's possible is necessary.
Okay, another question. You showed RGB and lambda 1, 2, 3. What kind of wavelength ranges do you cover?
Yeah, so since these are all silicon sensors, we are obviously going from 400 to 1050 or so nanometers. In the filter technology, we have a number of options, and it really depends on the requirements of the technology. In the line scan devices, it's a lot easier to apply customized filters because you have more space for the filter. It's not so difficult. So we can actually make filters for pretty much any range in the visible silicon range. I mean, in different sensors, we can do different filters, but in CMOS, we can. I showed, for example, the multi-field concept where we have effectively green, red, and blue filters, but we have very sharp bands and very defined spectral ranges. That looks quite different from a normal RGB Bayer type filter. So there's a lot of room for architecting these filters. Challenges come when you want to do more than a few. Yeah. Right, so 3 to 5 is maybe okay. After that, it gets more difficult. You have to deploy different technologies.
Okay.
Yeah.
Okay. Okay. Then that's it. Thank you very much.
Thank you very much.